All right, so the second lecture here is sort of why measure stress as a tensor, or um, why use stress tensors. And there's a very, very, very strong reason why, and it all goes back sort of to our Mohrs Circle problem. So we're going to revisit Mohrs Circle here. All right, so if you remember our problem originally, we had an element that maybe was being stressed underneath some principal direction. So this is just our 2D element. We'll call this x, and we'll call this y. And here we had some stress in x, and we had no shear. All right, so tau xy is equal to 0. And on our other surface, we had sigma y is equal to 0. And here, sigma x is equal to some number. Let's just, for the purposes of this example, we'll say 100 megapascals. So we can put that in terms of Mohrs circle. We have some normal stress relationship, some shear stress relationship. Off of this surface here, we have 0, 0. And off of this surface here, we have 100, 0. And so we have 2 points on Mohrs circle. Oops. 100, 0. And here, sort of 0, 0. Right? And since I'm an illustrator this time, I get the advantage of being able to draw a very, very good circle. Right. And Mohrs circle is going to look something like that. All right. Oops. There we go. All right. And of course, as we rotate through our given element here, right? So as this element rotates, we'll just do one rotation here, since this is review of last section's material. Right? We can end up causing stresses on all the different surfaces. Right? Based upon some angular rotation here. And of course, Mohrs circle is rotating at twice the rate of our element. So this is going to be 2 theta, and this will be the stress associated with that rotation. Okay. Part of the reason why the equation that you guys plugged into for Mohrs circle and the radius of that circle didn't end up working is in this particular example here, since it's rotated, right? Remember, you had the exam problem, right, where it was being loaded like this, and so this is our 0 rotation. We had 400 megapascals and 0, so this element looks like this, right, 400, and then it ends up failing at some angle here, and if we look at the element, we solved for this stress and this stress, but if we come down to this particular element, yes, you have your failure plane and some stress, some shear stress on that failure plane as well. But the thing that happens here is that this element right here is not equal to 0 anymore. So for those of you that plugged into that equation, all right, this equation here for the radius of it, you plugged in here, probably plugged in a 0. You only solved for sigma x here, which I think was 373, and tau xy which is 100, and you probably plugged in a 0, but sigma y in this rotation is not equal to 0. If you plug in what sigma y actually is, you'd have to go through and calculate it for this particular rotation. But as this thing rotates, there is actually a stress on the other side right here, which is also associated with this shear that you calculated. So out here we have 373, 100, right? And over here in the other side of this element, so you calculated this side of the element, 373, 100, but this 100 is associated with another force over here, which is not 0. Okay, you can end up calculating it out. I think it's like 27, 100. And if you plug in 27 into this equation, and don't quote me on that, you can actually go through and calculate it, you will actually end up getting the radius of 200 exactly, which then will cause this circle to go through 0, 0. So that's a little bit of a review from the exam. But at the 0 location, we have 0, 0 for one side, we have 100, 0 for the other side, or 400. Let's just go ahead and switch it to 400. 400 is our exam problem. Now 0, 0, and 400. We rotated it in the exam. It was 15 degrees. It rotates up here. We get 373, 100, and on the other side, it ends up being something like 27, 100, not 0, 100, because this element has some stress on that axis. All right. So that's our 2D Mohrs circle problem. We've now introduced stress as a tensor, so it's working in 3 dimensions. So let's go ahead and draw a 3-dimensional element. Okay. And I'm going to put all sorts of stresses on this element. Actually, let me compress it in this direction. Stretch it in this direction. Doesn't matter. I'm going to draw a whole bunch of them on here. It's going to look really, really crazy. Right. Lots of arrows, hard to read. Doesn't matter. I'm going to tell you that it can be represented by this stress tensor right here. Let's say in X it was maybe 100, in Y maybe 150, and in Z let's say it was negative 200, and then maybe our shear was 150, making this up as I go along, 75, 75, and then maybe 125, 125. All right, actually that may not converge, so let me switch this to 50. That way I make sure that my example actually ends up working out. So this is the stress tensor that describes this particular element. And now just imagine with me for 1 second. Let's just take the front face of this. All right, so I'm going to change colors here to red, and I'm talking about, sorry about that, change colors here to red. Talking about really this front face. So let me look at the very front of this element. Okay, and I'm gonna bring it here. Okay, and this particular element had some stress on the top, stress on the side, stress like this, like this, this, like this. And so you can imagine that this element, this particular problem here for this very, very front face, I can rotate this thing around to some angle where these shear stresses drop out. So there is some angular rotation where we only have normal stresses on the given face and there is no longer any shear. This is exactly the same case as up above. There is some rotation of a single 2D element where a no shear condition exists. So if I just look at one particular surface, I can come up with some rotation where the shear is going to drop out. Now, of course, these are going to increase or decrease, and these are going to increase and decrease, but there is some rotation that exists. In the same way, I can rotate the other sides of the surface and other sides of the surface until there is some element that only experiences normal stresses. Whatever those may be, positive or negative. Okay, so some rotation exists of this three-dimensional element where shear is completely gone. Some rotation exists where the shear on each surface is equal to 0. So how do I solve for that? And if you don't remember vector calculus, this actually ends up being a relatively simple problem. Switch back to black. And take my stress tensor. And let me see what it was up above. 150, 75. Okay. So remember, this is position. We'll say position 1. Right. So I can rotate this thing in some way where these terms all become 0. And these terms are going to either increase or decrease to some matrix that looks like, I'm going to label this as stress tensor P. This is going to be a number, and get 0, 0, 0, 0, 0, 0. Right? How do I actually get from position 1 to this unique position of no shear? Okay. Well, those of you that remember your vector calculus know that this is really an eigenvalue problem. So if you heard the word eigenvalue and thought you'd never need to use it again, sorry. Extremely important here. If you don't remember what an eigenvalue is, these are basically eigenvalues right here. So if you can take this matrix and solve for it in order to get its eigenvalues, you can determine what these stresses are here. And they end up being very, very important for the material properties of a matrix, because this tells you what happens in the zero shear condition. All right, so what is an eigenvalue? So to determine eigenvalues, you have to solve this particular equation right here. So we need to take the determinant of the stress tensor minus lambda times the identity matrix and set it equal to 0. What is lambda? Lambda is your eigenvalues. All right. 3 by 3 is a little bit difficult to do by hand, but we can go ahead and show you it for a 2 by 2. So we'll take our test problem here. Okay, in our test problem, remember our stress on the failure plane was equal to 373. Our stress, shear stress was equal to 100, And then that off axis, if we had gone through and solved for it, I believe is equal to 27. Right. So we can set this up in a two-dimensional stress tensor as well. We'll just do sort of the top half of it. So Rx, tau xy, tau xy, sigma sub y. Okay. So in this particular instance, I'm going to have my stress tensor here. Oops, let me increase my artboard. Just going a little long. All right, so I have this determinant up above. I'm just going to go ahead and do that. So here I have 373, 100. This is all coming from this stress tensor here. 127. I'm going to subtract lambda times the identity matrix 1, 0, 0, 1, and solve this relative to 0. This basically solves out as, I can combine it all. Oops, this is an equal sign here. And then, again, I'm going to take the determinant of all of this. Okay. This simplifies down as 373 minus lambda times, not times, 100, keep it in matrix form here, 127 minus lambda. And again, I need to take the determinant of this particular matrix and set it equal to 0 and solve. All right. Determinant of a 2 by 2 is actually somewhat doable. It ends up being just this minus this. All right. So in the full form, it would be, take this determinant, it would be sigma x minus lambda times sigma y minus lambda. Okay, so this is this times this minus this times this. So tau xy squared equal to 0. And here I'm solving for lambda. So in our particular example, I have 373 minus lambda times 27 minus lambda minus 100 squared equal to 0. All right. I can solve this all the way down. Right. I can basically FOIL this out. Again, I'm going to work off of this one here. Sigma x, so that I can follow my notes. Sigma x, sigma y, minus sigma x lambda, minus sigma y lambda, plus lambda squared, plus tau xy squared equal to 0. And I can solve this all the way down, and basically there's two solutions to this. Lambda 1 ends up being equal to sigma x plus sigma y divided by 2 plus 1/2 square root of sigma x squared minus 2 sigma x sigma y plus sigma y squared plus 4 times tau xy. And then the alternative solution, which is just the mirror of this, sigma x plus sigma y divided by 2 minus 1/2 sigma x squared minus 2 sigma x sigma y plus sigma y squared plus 4 tau xy, and rewritten it can actually be written as an equation, which some of you will recognize and groan at because it was on your first equation sheet, but we hadn't covered it in great detail yet. Sigma 1 is equal to sigma x plus sigma y over 2 plus the square root of sigma x minus sigma y over 2 quantity squared plus sigma xy quantity squared, and lambda 2 is equal to sigma x plus sigma y divided by 2 minus the square root of sigma x minus sigma y over 2 quantity squared plus tau xy quantity squared. So for the 2D problem here, those end up being your two eigenvalues, and you will recognize this as the center of Mohrs circle plus or minus the radius of Mohrs circle. So I can go back up to the beginning. I'll just redraw it here for the purposes of this space. I'll pretend like I don't know it goes through 0 and 400. Instead, I'm going to take one side of my element, which is drawn here, 27, 100, and the other side, which is 373, 100. Draw those 2 points. The center of my circle ends up being right there, and then plus or minus the radius. There's the radius to get out to those points, but plus or minus the radius would just be right there or right there. And imagine it's a circle instead of an oval, and there you get lambda 1, and there you get lambda 2, 0, and 400 in our particular example. You can go through and solve it out above. If you wanted to, you should land down at, if you solve this out, you should get lambda 1 equal to 0, or I'm sorry, lambda 2 equal to 0 and lambda 1 equal to 400. If that 27 is correct, and I'm pretty sure it is. Right? And you'll get the other one being 0. All right. So why does this all matter to the 2-dimensional or to the 3-dimensional case? Well, there's another way of solving this, which ends up being the way most people would do it, is rather than actually trying to solve these equations by hand, I'm going to start from this particular matrix right here on my stress tensor and this eigenvalue problem right here. And I'm just going to simply say, well, rather than doing this all by hand, oops, trying to extend that down. Rather than doing this guy all by hand and trying to solve the determinant of the stress tensor minus this set equal to 0, I have this other alternative in MATLAB where I just type in EIG or EIG, and it's going to tell me what lambda 1 and lambda 2 are. All right. In fact, it doesn't matter to MATLAB whatsoever whether the stress tensor is a 2x2 or a 3x3 or a 4x4 or a 5x5 or 6x6. As long as it's a square tensor, it's going to spit out as many eigenvalues as I want. And so, in fact, if I take the 3-dimensional problem, right, which up above, I'm just going to hit copy and paste. put X's through everything. Doesn't actually matter whatsoever to MATLAB at all. I can just type in this matrix and then say, hey, what is the eigenvalue of R? And it's going to give me lambda 1, lambda 2, and lambda 3. So let's just go ahead and do that real quick. Let me get MATLAB started up. All right, I went ahead and pulled open MATLAB here. If I can get both on the screen at the same time, this might take me a second. We can go ahead and do this. All right, let's go ahead and type in that stress tensor. So call stress is equal to 100, comma 50, comma 75, and then 50, comma 150, comma 125, and then 75, comma 125, comma negative 200. And hopefully I actually wrote one that's symmetric, and it looks like it is. And hopefully I also wrote one that's physiologically possible, or actually physically possible. Let's go ahead and run the eigenvalues on that. We're going to find out here in a second. Oops. There you go. And it tells me that my eigenvalues does actually converge, so thank goodness. I was smart enough to write one that was solvable. It's negative. We'll just go ahead and round. We'll say negative 250, 70, and 230, just for the purpose of this example. You can be more precise obviously in your homework. So our eigenvalues are negative 250, 70, and sorry, I forgot that other one, 230. So what does this mean? Well, it means that there's some position that I can rotate this stress tensor to that will form another stress tensor, which we call our principal directions, that is equal to this tensor exactly, which is, it doesn't matter which order I put them in, 250, 70, 230, and on all the other directions there's a no shear condition. Well, if I wanted to extend this down to Mohrs circle, right? So I'm going to extend this down to Mohrs circle. Some point down here at negative 250, some point here at 70, and some point here at 230, right, where there's no shear whatsoever occurring. And I can now draw what's called the three-dimensional Mohrs circle. And again, I'm going to cheat. And there we go. All right. So essentially there are three different angles that we can rotate around. So remember, we have a three-dimensional element. My drawing tool back out. Okay. And at the first one, we were in some rotation where there was shear and all sorts of crazy stuff happening in all the different surfaces, and stress and stress and stress and so forth, right? We can rotate this element into some other position where we only have principal stresses or only have normal stresses acting on it. This happens to be this zero shear condition. Remember, this is tau, this is sigma for our axis. So there's some zero shear condition, right? No shear, where only normal stresses are occurring, or lambda 1, lambda 2, and lambda 3. Right. Those plot on here, lambda 3, lambda 2, lambda 1, and I can draw circles through them, which basically means if I rotate about one of these axes, so here, let me just say this is lambda 1, so as I rotate about lambda 1, all right, lambda 1 ends up staying exactly the same, right? So if I rotate around lambda 1, this is going to be a lambda 1 rotation, right? I'm going to go around this circle right here, and lambda 2 and lambda 3 are going to change, right? So if I hold lambda 1 constant and I just rotate around this way, which ones are going to change? Lambda 3 and lambda 2 are. Same way if I hold lambda 2 constant and rotate around it. So here I'm going to hold lambda 2 constant, right? So this is going to hold lambda 2 constant. I'm going to rotate around it. Which ones are going to change? Well, lambda 1 and lambda 3 are going to change, right? So it's the big circle around the outside. If I hold around lambda 3, or if I hold lambda 3 constant and rotate around it, so here lambda 3 and rotate around it, which ones change? Lambda 1 and lambda 2, or those stresses end up changing, and I end up with shear on those particular surfaces as well. So essentially, what we just have derived is all the internal stresses that can occur within a material based upon its 3D architecture. So we did it with 2D before. Now we've done it for 3D. And this is where the stress tensor ends up becoming incredibly powerful, because by solving for this tensor right here, creating this tensor right here, we can then convert it into a principal stress tensor, or the principal stresses, and those principal stresses then tell us every internal stress that can occur within the given material for different rotations. So a single stress tensor can be converted into principal stresses and can be converted into the internal stresses that the material then has within it. So this is right here 3D Mohrs circle. Right. So what's the maximum shear within this element? Right here at the very, very peak. Right. Or if I have something that is maybe anisotropic, then maybe I care about the other maximum shears as well. This is max shear for lambda 2 rotation and max shear for lambda 3 rotation. All right, so clearly this can tell you a lot of different interesting things about our internal stresses. Right, real quick. So some elements to kind of tie everything together. If I think about a material that's isotropic, all right, so it's the same in all different directions, then I probably don't really care about this shear or this shear and how it might fail on my material, because remember, it's the same in all possible directions. So really only this one max shear element ends up mattering to me, or this lambda 2 rotation, or the middle eigenvector. So as typically when we write our eigenvalues, we go from MATLAB will typically spit them out from smallest to largest. I actually labeled this incorrectly. This should have been lambda 1 to lambda 3. Right, so this is going to be our smallest. This is going to be our largest. Okay. So as we rotate around lambda 2, these are the two that are going to be the farthest away from each other. So our maximum shear condition just ends up being lambda 3 minus lambda 1 divided by 2. Okay. And for an isotropic solid, that's really the only one I care about. But if you imagine something that's transversely isotropic or orthotropic, and now all of a sudden our material properties are not the same in every single direction, well, you could have a failure shear for an off-axis rotation, that ends up actually failing your material, right? So it could be really strong against shear in one direction, and if we align that with the max shear condition, well, we may not fail at this max shear, but we may end up failing due to these transverse shears here and here. So all of a sudden, those things end up making a much sort of bigger impact on our material. So again, if you think about something that's transversely isotropic, not the same in all direction, all of a sudden these off-axis internal shears could end up having a major role in whether a material will fail or not. All right, so that's really the most important lecture from the second week, is this concept of the stress tensor, and then how the stress tensor ends up being very, very valuable for 3D internal mechanics.